Let's start with the first question. What is energy? I notice that when I ask this question to students, they usually have trouble giving an exact definition. And I must say it is not easy. The scientific definition for energy would be something like the capacity of a system to perform work. We humans use energy to do some work. We use energy for heating air and water. We use energy for transportation of people and products by cars, trains, trucks and planes. We use energy to produce food and products. We use energy to illuminate houses and streets. We use energy to watch TV, do our laundry, working on computers and surfing the internet. At the moment, you are consuming energy by watching this video lecture. Energy appears in many forms in our daily life, like gravitational energy, kinetic or mechanical energy, electrical energy, heat radiation, wave energy, chemical energy and nuclear energy. The total amount of energy is always conserved. The form of energy may change in time, but the total amount does not change. This means that if we want energy to work for us, we usually convert it in one form to another form. An example is the electric motor. This is a tool in which we convert electrical energy into mechanical energy. The unit of energy is joule. Power is the energy per time and is expressed in watts. 1 watt is 1 joule per second. In this course, we will use a more practical unit, which is generally used to express the electrical energy, kilowatt hours. 1 kilowatt hour equals the energy of a power of 1 kilowatt being used for 1 hour. 1 kilowatt hour equals 3.6 million joules. The world as we know today is based on the capability of humans to convert energy from one form to another form. The most prosperous and technological developed nations are also the ones which have access to and are using the most energy per capita. Therefore, many people believe that the biggest challenge for humankind in this century is tackling the energy problem. Why do we have a problem? The first challenge the humankind is facing is a supply-demand problem. The demand is constantly growing. The world population is still rapidly growing, and some studies predict a world population of 9 billion around 2040 in reference to the 7 billion people living on this planet today. All these people will need energy, which increases the global energy demand. In addition, the energy consumption per capita is linked to the living standard of a country. In 2010, in the US, around 230 kilowatt hours of energy per capita per day was used, whereas countries in Africa, like Nigeria, only used 1/10 of this energy, around 23 kilowatt hours per day per capita. In this graph you see the living standard expressed in Human Development Index. The darker color, the more developed the regions are. However, the light colors in these figures are getting darker by the year. In many countries, the living standard is rapidly increasing, like China and India, where approximately 2.5 billion people are living. These people represent more than 1/3 of the world's population. Both increasing world population and increasing living standards will increase the energy demand. The International Energy Outlook 2013 predicts that the energy consumption will increase by 56% by 2040 in reference to 2010. The increasing demand in energy has economic impact as well. If there is more demand for a product, while supply does not change much, the product will get more expensive. This is also true for energy. As an example, we show a plot of the annual average price for an oil barrel normalized to the value of the 2008 US dollar. First, you can see that prices went up during the oil crisis in the 70s. In this decade, some countries stopped producing and trading oil for a while. The second era of higher oil prices started at the beginning of this millennium. Due to the increasing demand from new growing economies, the oil prices have been significantly increased. A second challenge that humankind is facing is related to the fact that our energy infrastructure heavily depends on fossil fuels like oil, coal and gas. Fossil fuels are nothing but millions and millions of years of solar energy stored in the form of chemical energy. The problem is that humans deplete these fossil fuels faster than they are generated through the photosynthetic process in nature. Therefore, fossil fuels are not a sustainable energy source. In the coming century, we will see that we are running out of the oil and gas reserves if we continue our current rates of consumption. Another barrier is that it is technologically more challenging to get the fossil fuels out of the reserves currently left. Governments and companies are willing to take higher risk, like we have seen in the Gulf of Mexico spill in 2010. A third challenge is that by burning fossil fuels, we produce the so-called greenhouse gases like carbon dioxide. The additional carbon dioxide created by human activities is stored in our oceans and atmosphere. Here you see the increase in carbon dioxide concentration in the Earth's atmosphere up to 2000. Most scientists think the increase in carbon dioxide is responsible for the global warming and climate change, which can have drastic consequences of the habitats of many peoples. Therefore, humankind is looking for alternative energy sources like solar and wind. As I mentioned earlier, energy appears in nature in several forms. We humans make energy work for us by converting it from one form to another form. Let's consider fossil fuels. How are fossil fuels converted into other forms of energy? I will illustrate that in the following simple diagram. By burning fossil fuels, roughly 90% of the chemical energy is converted into heat. Using heat engines, thermal energy can be converted into mechanical energy. Heat engines have a conversion efficiency of up to 60%. The far majority of the current cars and trucks are based on this principle. Mechanical energy can be converted into electricity using electric generators with an efficiency of 90%. This shows that in all process steps of making electricity out of fossil fuels, at least 50% of the initial available chemical energy is lost in the various conversion steps. Chemical energy can be directly converted into electricity using a fuel cell. The most common fuel used in fuel cell technology is hydrogen. Typical conversion efficiencies of fuel cells are 60%. A regenerative fuel cell operates in the reverse modus and converts electrical energy into chemical energy. Such an operation is called electrolysis, and the device operated in such mode called electrolyzer. Typical conversion efficiencies of hydrogen electrolyzers of 50–80% have been reported. Another route of making electricity is based on an alternative fuel, nuclear energy. Nuclear energy is the energy generated in nuclear fission reactions and generates heat as well. This can be converted in electricity using the just introduced heat engines and electric generators. Next, we will look at alternative energy conversions, which are not based on fuels. Hydroelectricity is one example. This potential energy of rainwater falling in mountainous areas or elevated plateaus is converted into mechanical energy using dams. Using so-called tidal pools, the potential energy stored in the tides can also be converted to mechanical energy and subsequently electricity. The kinetic energy of wind can be converted into mechanical energy using windmills. Finally, solar energy can be converted into electricity as well. If solar light is directly converted into electricity using devices based on semiconductor materials, we call it photovoltaic. Photo means light and voltaic means electricity. Typical efficiencies of most commercial modules are in the range of 15 to 20%. Solar light can also be converted into heat. This is what we call solar thermal energy. Examples are heating of water flowing through a black absorber material that is heated in the sunlight. This heat can be converted into electricity again using heat engines. As the conversion efficiency of heat engines strongly depends on temperature, concentrated solar power systems are used to generate electricity through solar heating using so-called high-temperature collectors. Next to generating heat and electricity, solar energy can be converted into chemical energy as well. This is what we refer to as solar fuels. This is possible by using photovoltaics and regenerative fuel cells, but solar light can also be directly converted to fuels using photoelectrochemical devices. This means we can convert solar energy into electricity, heat, and chemical energy. In weeks 2 to 5, we discuss the photovoltaic conversion. In week 6, we will discuss the solar thermal and the solar fuel route. Renewable energy sources are energy sources that are replenished by natural processes at a rate comparable or faster than its rate of consumption by humans. Consequently, hydro, wind, and solar energy are renewable energy sources. Fossil fuels and nuclear energy are not renewables, as their fuels are consumed faster than they are generated in nature. From all the energy sources based on chemical, thermal, nuclear, hydro, wind, solar, and geothermal, roughly a third is being used to generate electricity. Electricity is a form of energy that can be easily and cheaply transported with relatively small losses through an electric grid. We might not realize it anymore, but electricity has made today's modern society possible. It is a symbol of modern life and progress. Electricity has been practically used for more than 100 years now. Electricity provides us the energy to cook food, to wash, to do the laundry, illuminate the houses and streets, watch TV, air condition and heat, work on a computer and surf on the internet. The access to electricity determines the living standard of humans. We must realize that around 1.2 billion out of the 7 billion people worldwide still do not have access to the electricity grid. The electricity worldwide is mainly generated from oil, coal, gas, nuclear and hydropower. Here we see the relative contributions of these sources to the global electricity generation in 2007. 65% of the electricity is coming from fossil fuels, where coal is the dominant contributor. Unfortunately, coal produces roughly 2 times more carbon dioxide per generated unit of energy in reference to gas. Nuclear is responsible for 16% of the world's electricity generation, and hydropower is with 90% by far the largest contributor among the renewable energy sources. In the conversion from chemical and nuclear energy to electricity, 2/3 of the energy is lost. 1/3 ends up in the form of electricity. 40% of the electric energy is used for residential purposes and 47% is used by industry. 13% is lost in transmission. As you can see, in 2007, transport did not play a significant role in the electricity consumption. However, it is expected that transport-related electricity consumption will increase in the coming decades as well. In 2007, 20,200 terawatt-hours of electricity was generated worldwide. If you consider a 0.5 gigawatt nuclear power plant, it means that we need around 5,000 nuclear plants around the world if our electricity needs would be fully covered by nuclear power. Realize that sources for electricity generation might differ from country to country. For example, in the Netherlands, electricity generation heavily depends on the local gas resources, whereas in Brazil, hydroelectricity is the most important resource. In the last 100 years, humankind's energy infrastructure heavily relied on fossil fuels. We are quickly using the solar energy of millions and millions of years, converted into chemical energy by the photosynthetic process and stored in the form of gas, coal, and oil. How did we do that before the Industrial Revolution? The main source of energy back then was wood and biomass, which is a secondary form of solar energy. The energy source was replenished in the same characteristic time as the energy being consumed. In the pre-industrial era, humankind was basically living on a secondary form of solar energy. I'm not claiming that this energy consumption was a fully sustainable way of living. We have to take in mind that deforestation due to increasing population density was already playing a role at the end of the first millennium in Europe. The sun has been the energy source for all the processes on the surface of a planet. Wind is a result of temperature difference in the atmosphere induced by solar irradiation. Waves are generated by the wind. Clouds and rain are initially formed by the evaporation of water due to sunlight. As the sun is the only real energy source we have, we need to move back again to an era in which we start to utilize the sun to satisfy our energy needs. In this course, I will introduce you to that technology. So how can we get electricity directly from sunlight? The mechanism in which solar light is directly converted into voltage or current is called the photovoltaic effect. In week 2, we will discuss the photovoltaic effect in greater detail. But to give you a first idea, I will show its principle using this simple animation. Here we see a simplified representation of a silicon-based solar cell. It consists of the crystalline silicon absorber layer, a p-ion junction to separate the light-excited charge carriers, and a metal front and back contact. Here we see the same structure, but then in a cross-sectional view. The light enters the solar cell from the front side in this illustration, that is the top side. The light is transmitted into the absorber layer, where its energy is absorbed. The energy is used to excite charge carriers in the semiconductor material, which are a negatively charged electron indicated by the red dot and a positively charged hole indicated by the blue dot. These charge carriers diffuse around and need to be separated, which occurs at the depletion region between the N and p-doped silicon and the depletion region at the back of the solar cell. You don't have to understand yet why this happens. I will explain this in detail next week. Then the charge carriers have to be collected at the contacts. In this example, the contacts are connected with a load, in this case, a lamp. The electron will move through the load back to the solar cell. Both charge carriers recombine at the metal p-layer interface. It shows that the photovoltaic process is based on three important principles. The first is excitation of free mobile charge carriers due to light absorption. The second is separation of the charge carriers. And the third one is collection of the charge carriers at the contacts. A variety of PV technologies exist today. We can categorize them in various ways. The first logical way is to categorize them based on the type of absorber material. We will do that in a minute. Another categorization approach is based on degeneration, which is often used in books about PV technology. I have some personal objections against the generation-based categorization, but as it's widely used, I will introduce it here. For that, we use the graph in which we plot on the horizontal axis the cost price of the solar cell per area expressed in dollar per square meter. So solar cells made of expensive materials or using expensive processing methods will be further to the right on this axis. The conversion efficiency is the fraction of the energy in the solar light which is converted into electricity, which is represented by the vertical axis. The efficiency scales with the energy yield of the solar cell. The larger the efficiency, the larger the generated power per area will be. This power is expressed in watts per square meters. For example, standard test condition for solar cells means an irradiance of 1000 watts per square meters. This means a solar cell with conversion efficiency of 10% produces under standard test conditions a power output of 100 watts per square meters. It means that the slope of the dashed line is equal to the watt per dollar, or in other words, it's reciprocally linear with the cost price per watt peak. The cost price per watt peak corresponds to the cost price of the energy generated by the solar cell. In this example, the dashed line represents $0.50 per watt. If the slope of these dashed lines is very steep, the cost price per watt is low. Whereas when the slope of the dashed lines becomes less steep, the cost price per watt peak is getting significantly higher. To compete with other energy sources, you would like that your PV technology overlaps with the steepest lines in these graphs. The first generation PV technology is based on using very pure bulky semiconductor materials, like crystalline silicon. Pure materials means less defects, and in general, solar cells with a relatively high efficiency can be manufactured. However, high quality materials requires more expensive production processes, which in general makes the cost price per area solar cell larger as well. The light gray circle roughly shows the area in which you would find the first generation PV technology. What is the second generation PV technology? These are PV devices which are firstly based on thin film solar cells. Thin film implies that less material is used, which makes the solar cells cheaper. Secondly, these solar cells are manufactured using cheaper processing technology. As a consequence, the materials have more defects, resulting in lower performances. Although the solar cell's efficiency is lower due to the lower cost price per area, the cost price per watt of the second generation PV technology is significantly lower. The blue area represents the so-called Shockley-Queisser limit, which will be introduced in week 3. Given the shape of our solar spectrum and the band gap of the materials used, the Shockley-Queisser limit tells us the theoretical maximum conversion efficiency of the solar cell. Third generation PV technologies are based on solar cell concept which try to tackle the Shockley-Queisser limit. So third generation PV technology would be solar cell with higher conversion efficiencies in reference to the first and second generation. The current solar cell concepts being studied to beat the Shockley-Queisser limit will be discussed in week 6. Furthermore, the cost price of the materials and processing techniques used to process the third generation solar cells are expected to be cheap as well. The result is that the third generation solar cell technology overlaps with the steepest dashed lines in this graph, meaning that third generation technology would have the lowest cost price per watt peak. However, beating the Shockley-Queisser limit for most concepts is a challenge itself. Making these complex concepts cheaply is a completely different ballgame. Next to categorizing the PV technologies in the 3 generations, we indicate the various PV technologies based on the semiconductor material used as absorber layer in the solar cell. The most dominant PV technology is based on crystalline silicon wafers. This technology represents around 90% of the current PV market and belongs to the first generation PV technology. We will discuss this technology in great detail in week 4. Another PV technology based on silicon is thin film silicon. In this case, no crystalline silicon wafers are used, but very thin layers of silicon which are deposited on glass or a flexible substrate. The silicon does not have the same lattice structure and can be amorphous or nanocrystalline. This technique belongs to the second generation PV technology and will be discussed in week 5. An alternative thin film PV technology is based on 2,6 semiconductor, the cadmium telluride. Cadmium telluride PV technology belongs to the so-called second generation technology as well. The cadmium telluride has currently the largest market among the thin film PV technologies. In week 5, we will discuss this technology in great detail. Another thin film PV technology based on a chalcogenide alloy is CIGS, which stands for copper, indium, gallium selenide. Among the thin film PV technologies, it has the highest demonstrated conversion efficiency on lab scale, just above 20%. It belongs to the second generation PV technology as well. Another thin film PV technology is based on organics, also referred to as the plastic solar cell. The absorption and charge transport in the solar cell occurs in conductive organic polymers or molecules. The dye-sensitized solar cell is a kind of photoelectrochemical system in which a semiconductor material based on molecular sensitizers is placed between a photoanode and an electrolyte. We will discuss both the organic and dye-sensitized PV technology in week 5. The final PV technology we will discuss is based on 3,5 semiconductor materials, such as gallium arsenide. 3,5 materials are being used in multi-junction devices, often processed on germanium wafers as substrate. The multi-junction based on 3,5 semiconductors are the most efficient solar cells today. The record conversion efficiency of 44% was obtained with a metamorphic triple junction in 2012. The 3,5 semiconductor solar cells are being used in concentrator PV technology and in space applications. This technology will be discussed in week 5. Third generation PV technologies are based on various concepts trying to beat the shock-likewise limit. We will discuss third generation concepts in great detail in week 6. Third generation PV technology covers a wide range of novel and innovative ideas, the most successful being multi-junctions. You have to realize that most of these ideas still need to be proven. Some of these ideas are quantum dot solar cells, absorber layers exhibiting multiple exciton generation, intermediate bandgap solar cells, hot carrier solar cells, spectral conversion using down converters or up converters. Finally, I show you here the famous chart of NREL. It summarizes the worldwide research effort of the last 40 years, and it shows the current record efficiencies of solar cells at research scale. These solar cells are fabricated in lab environment and have very small sizes, often not larger than 1 square centimeters. The purple colored markers represent the 3.5 technology based on single, double and triple junctions and have efficiencies ranging from 26% up to 44% under concentrated light conditions. The blue lines and dots represent crystalline silicon technology based on monocrystalline and multicrystalline silicon. The record efficiency ranges from 20 up to 25% under standard one-sun illumination conditions, and 27% can be achieved under 92 suns illumination. The inorganic thin film technologies like thin film silicon, cadmium telluride and CIGS are indicated by the green markers, and their record efficiencies range from 13.4% up to 20%. The red colored lines and markers indicate the emerging PV technologies, like organic solar cells. You have to be aware that these are lab results of very small area solar cells, and this chart does not tell you anything of the long-term stability of some PV technologies, certainly not the ones indicated in the red. They indicate the potential efficiency of many PV technologies. Nevertheless, you have to realize that most PV technologies still have a large gap between the record conversion efficiencies of the lab cells and the conversion efficiency of large commercial modules. It will be my pleasure to discuss these challenges in week 4 and 5. What is the history of solar energy technology and what is the current status of PV technologies in the real world? I mean the world of large area modules. I will discuss that in the next 2 blocks. I will begin with the history. In this block, I will give a quick overview of the development of solar energy technology. Know that this overview will be far from complete. If you are interested in a more detailed overview, I advise you to search on the internet, where you will find many good historic overviews. As early as the 7th century before Christ, humans have used the first solar technology. They used magnifying glasses to make fire. Later, the Romans and Greeks used concentrating mirrors for the same purpose as well. In the 18th century, Horace de Saussure built heat traps, which are a kind of miniature greenhouses. He constructed hot boxes consisting of a glass box with another bigger glass box, up even to 5 boxes. When exposed to direct solar irradiation, the temperature in the inner bottom box rose up to 108 degrees Celsius, warm enough to boil water and cook food. These boxes can be considered as the world's first solar collectors. In 1839, the scientist Edmond Becquerel, at an age of 19 years, discovered the photovoltaic effect. The photovoltaic effect is the generation of voltage or current in a material when exposed to light. He observed this effect in an electrolytic cell. The cell was made out of 2 platinum electrodes placed in an electrolyte. An electrolyte is an electrically conducting solution, and in this case he used silver chloride placed in an acidic solution. By shining light on it, he observed that the current in the cell was enhanced. In the 60s and 70s of the 19th century, the French physicist Auguste Mouchet was developing solar-powered steam engines. He believed that the coal resources were limited. He developed the first parabolic trough solar collector. As coal became cheaper, the French government decided that solar energy was too expensive and stopped funding Mouchet's research. William Grills Adams and Richard Evans demonstrated in 1876 that a junction based on platinum and the semiconductor selenium shows the photovoltaic effect. However, the performance of the device was too poor. 7 years later, Charles Fritz managed to make a PV device based on a gold-selenium junction with a light-to-electricity conversion efficiency of 1%. In 1887, Hertz discovered the photoelectric effect, which is the effect that some charged objects, when exposed to ultraviolet light, lose their charge faster. In 1905, Albert Einstein published a paper in which he explained the photoelectric effect with assuming that light energy is being carried with quantized packages of energy. Nowadays we call these packages photons, which we will discuss later this week in great detail. For this paper, Einstein received the Nobel Prize in 1921. In 1918, the Polish scientist Jan Czochalski developed a way to grow single crystalline silicon, a technique of great importance for the solar cell technologies based on crystalline silicon wafers, which has been developed in the second half of the 20th century. In week 4, we will come back to this processing method. In 1932, the photovoltaic effect was discovered in the 2,6 semiconductor material cadmium sulfide by Audobert and Stora. In week 5, we'll come back to solar cells based on 2,6 materials. It took up to 1953 for the potential performance of solar cells made of various materials with various band gaps to be estimated. Dr. Dan Trivich of the Wayne State University performed theoretical calculations in reference to the solar spectrum. In week 3 of this course, we will come back to such estimations. The real development of modern photovoltaic devices as we know them today started at Bell Labs. In 1954, Bell Telephone Laboratories produced a silicon solar cell with a light-to-electricity conversion efficiency of 4%, and they later achieved 11%. In the mid and late 50s, various companies and labs among US Signal Corp's laboratories, RCA Lab, Hoffman Electronics developed silicon-based solar cells to power orbiting Earth satellites. From 1958 and in the 60s, the progress in PV technology was driven by the energy demand of space technology. Various satellites in the series Vanguard, Explorer and Sputnik were launched with PV-powered systems on board. In 1962, Bell Telephone Laboratories launched the first solar-powered telecommunications satellite, whereas in 1966, NASA launched the first orbiting astronomical observatory powered by a 1 kilowatt photovoltaic solar array. In 1968, Professor Giovanni Francia built the first concentrated solar power plant near Genoa in Italy. The plant was able to produce 1 megawatt with superheated steam at 100 bars and 500 degrees Celsius. Note that these pictures do not reflect the plant in Italy. In 1970 in the Soviet Union, Zores Alferov develops the high-efficiency solar cell based on gallium arsenide heterojunction solar cells. This is the first demonstrator of a solar cell based on 3,5 semiconductor materials. We will discuss this technology in week 5. At RCA Laboratories, Dave Carlson and Chris Wronski developed in 1976 the first thin-film photovoltaic devices based on amorphous silicon. In 1978, in Japan, Sharp and Tokyo Electronic Application Laboratory bring the first solar-powered calculators on the market. In the 70s, due to the oil crisis and the increasing oil prices, the public interest in photovoltaic technology for terrestrial applications is increasing. PV technology is not only a niche technology for space applications anymore. In the late 70s and 80s, many companies start to develop PV modules and systems for terrestrial applications. In 1980, the first thin-film solar cells based on copper sulfide or cadmium sulfide with conversion efficiencies above 10% were demonstrated at the University of Delaware. In 1985, at the University of New South Wales in Australia, crystalline silicon solar cells with efficiencies above 20% were demonstrated. In week 4, the background and current state of high-efficient crystalline silicon PV devices will be discussed. In 1984 up to 1991, the largest solar thermal energy generating facility in the world was built. These 9 solar plants built in the Mojave Desert in California have a combined capacity of 354 megawatts. In 1991, the first high-efficiency dye-sensitized solar cell was published by the École Polytechnique Fédérale Lausanne in Switzerland by Michael Gretzel and co-workers. The dye-sensitized solar cell is a kind of photoelectrochemical system in which a semiconductor material based on molecular sensitizers is placed between a photoanode and an electrolyte. We will discuss this technology in week 6. In 1994, NREL in the US developed the concentrator solar cells based on 3,5 semiconductor material. The cell, based on a gallium indium phosphide, gallium arsenide based 2-terminal concentrator solar cell, exceeded the 30% conversion limit. The concentrator PV technology will be discussed in weeks 5 and 6. And at the end of the 90s, the total worldwide installed photovoltaic power reached 1 gigawatts in 1999. From 2000, solar energy entered the era in which environmental issues and economic issues renewed the public interest in solar energy. It is the era in which the solar market has transformed from a local market to a global market. In the new millennium, Germany took the lead with a progressive feed-in tariff policy, leading to a large national solar market and industry. In 2010, 43% of the worldwide installed PV systems were installed in Germany. From 2008, the Chinese government has heavily invested in the local solar industry and has become, in a few years, the dominant PV module manufacturer. In 2012, the worldwide solar energy capacity surpassed the magic barrier of 100 gigawatts installed power. This is 100 times more than the installed capacity 13 years earlier in 1999. This means the solar market has been annually growing with on average 40% for the last 13 years. Since 2008, installed PV power has shown an unprecedented growth and shows the potential of solar energy to soon become the largest energy source that is not based on fossil fuels. In the coming weeks, it will be my pleasure to introduce you to the energy technology of the future, solar energy. In this blog, I have given you a quick journey through the history of solar energy technology. In the next blog, we will look at its future. What is the current status of solar energy? First, I would like to discuss the production of solar modules. The figure shows the worldwide solar cell production. The vertical axis represents the annual production. We express the annual production in the total produced power capacity in megawatts. The horizontal axis represents time. The solar cell production is increasing exponentially every year. The red numbers represent the annual relative increase in production capacity in reference to the previous year. It shows that the production increases annually by more than 40%, which is an unprecedented growth. Secondly, this graph shows how the various PV technologies contribute to the global module production. The gray colors represent the wafer-type crystalline silicon PV technology. As you can see, the crystalline silicon PV technology is the dominant technology and contributes to around 90% of the total module production. The inorganic thin film PV technologies like amorphous silicon, cadmium telluride and CIGS are responsible for the remaining 10%. The next graph shows the worldwide cumulative installed PV power, which is exponentially increasing in time as well. The different colors reflect the different regions in the world. The green area corresponds to Europe, which shows that the far majority of PV systems are installed in Europe. The Asia-Pacific region, shown in light blue, is a good second, where most of the PV power is installed in Japan. The pink color corresponds to China, which shows an unprecedented increase in the installed PV capacity from 2010 to 2012. The purple area reflects the PV capacity installed in North and South America. Orange corresponds to the Middle East and Africa, whereas yellow corresponds to the rest of the world. It is important to note that the total installed solar power has passed the 100 gigawatt mark in 2012. Let's look for a moment in more detail to where the PV is installed in the world. This figure illustrates the relative contribution of various nations to the total installed PV power in 2012. Here we can clearly see that 31% of the total PV capacity is installed in Germany. This is a result of the German government's progressive feed-in tariff policy of the last 10 years. Considering that Germany lies within an area with a relatively low radiation level compared to the rest of the world, the large contribution of solar to Germany's electricity production shows the promising potential of solar energy for the sunnier parts of the world. The runner-up is Italy, which accounts for 60% of the worldwide PV capacity. China, with a contribution of 8%, is the fastest growing market at the moment. In 2010, China only contributed with 2% to the global PV capacity. The United States, Japan and Spain are the other countries in the top 6, with a relative contribution of 7 to 5% to the worldwide installed PV capacity. Note that after the Fukushima disaster, the Japanese government introduced some progressive feed-in tariffs to promote and speed up the introduction of renewable energy sources. An interesting aspect of PV technology is that it's not only a European affair. The local demand and supply has been changing rapidly in the last 13 years. This figure illustrates the evolution of the worldwide supply and demand of PV modules in the various regions around the world. Blue represents Europe, red represents the Asian Pacific, mainly Japan, purple the Americas, mainly the United States, and pink represents China. Let's start with the demand. This figure shows that in 2000, the biggest market with a total share of 40% was in Japan. From that moment, due to the introduction of various subsidy policies in Germany, Spain and Italy, the European market share increased up to 80% by the year 2008. Around this time, the PV market appeared to be a local European affair. From 2009, the domestic PV market in China, the Americas and Asia Pacific are increasing very rapidly as well, and catching up quickly with Europe. Now we look to the supply side. The Asia-Pacific share on the market was increasing. Up to 2006, the European share was increasing slowly. From 2008, we see a big growth of production in China, made possible by a huge investment of the Chinese government into scaling up PV module manufacturing in China. In 2012, around 60% of all PV modules were produced in China. In 2000, as you can see, the PV market was an essential local market mix. The local demand and supply in Asia, Americas and Europe were in balance. By 2012, no local balance between supply and demand exists anymore. The majority of the demand is in Europe, whereas the majority of the production is in China. You see that the PV market has transformed from a local market of demand and supply to a global market of demand and supply. Another aspect that controls demand is the cost price of PV technology. How does the cost price of electricity generated by a PV system compare to the electricity delivered by your energy company? To answer this, we have to look towards this learning curve. The learning curve is the graph which shows how the cost price, or in this case the sales price, is dropping in time. In time, the industry gets more experienced. Progress in technology provides for better PV modules with higher efficiencies. This experience results in better and faster processing, leading to higher production yields. Upscaling of production leads to lower cost of the source materials. Learning curves usually show an exponentially decreasing cost price in time until the technology or product is fully developed. In this graph, we have the average global sale prices of a PV module versus the cumulative installed power up to 20 gigawatts. Note that the points up to 20 gigawatt in the gray area are real data points up to 2009. The points in the white area are extrapolations of the general trend. Important to note is that the sales prices, discounting some fluctuations, follow a largely exponential decay. Currently, the average retail price of only PV module is below $1 per watt peak. Now we will see how the cost price of a PV system is not only determined by the module. The red dots show the decrease in the cost price of a complete PV system. As you can see, in the early days of the PV technology, the system price was dominated by the module price. However, in the current situation, the contribution of the non-modular components starts to play the most dominant role. With non-modular components, I refer to components like the racking, wiring, inverter, battery for stand-alone systems, or even maintenance cost. The difference between the red and green line corresponds to the non-modular cost and are indicated by the dark blue markers. This shows the learning curve of the non-modular components, which is dropping not as fast as the module price. This means that nowadays the reduction in cost price of a PV system will be mainly limited by the cost price of the non-modular components. This shows the advantage of crystalline silicon PV technology, which has higher module efficiencies ranging from 14 up to 20% in reference to thin film technologies. Higher conversion efficiency means higher yields per area. While the non-modular costs per area are the same, the cost price per watt peak of the non-modular costs will be consequently lower for modules with higher conversion efficiencies. In block 1.2 we have discussed that hydropower is responsible for 90% of the total worldwide electricity production and nuclear is 16%. The question now is, how do these numbers compare to solar? For that, I've constructed the following figure. On the vertical axis, you see the cumulative installed capacity, which is expressed in gigawatts of power. Note that this is a logarithmic scale. Here, we only consider the energy sources which are not based on fossil fuels. Light blue represents hydroelectricity, dark green represents nuclear, red represents wind, and dark blue represents solar. The installed nuclear power is hardly growing anymore, whereas the installed hydropower is still slightly growing in time. Wind is growing at a relative rate of 20% per year. As you can see, from 2008, solar is the fastest growing energy technology with a rate far above 40%. However, it's not fair to compare the installed power between technologies like this. The numbers given here represent the maximum power the energy source can produce, but it's not the average power the electricity source has delivered in reality. The relation between these two is called the capacity factor, which is basically a measure of how often an electric generator runs for a specific period of time. Nuclear has with 90% the highest capacity factor, followed by hydropower with an average capacity factor of around 40%. For wind energy, I have assumed an average capacity factor of 30%, and for solar, I have assumed a capacity factor of 15%. A low capacity factor for PV systems can be explained by the fact that for most geographical locations, almost half of the solar day is devoid of solar radiation at nighttime. If we use these capacity factors, we can look at the effective installed power of these electricity sources. Currently, solar energy generates an order of magnitude less electricity than hydro and nuclear. However, I claim that the trend in the growth of solar energy will continue the coming years. If we extrapolate the trend of the last decade, we see that the installed power of solar energy will exceed nuclear, wind and hydropower by the end of this decade. We know the shape of the solar spectrum. How is the spectral shape and irradiance of the solar light affected by the Earth's atmosphere? Let's consider that the Earth's atmosphere is 8,000 kilometers thick. The irradiance of the solar light arriving at the outer side of the Earth's atmosphere is approximately 1,350 watts per square meters. In this figure, the spectral power density of the irradiance arriving at the outer side of the Earth's atmosphere is shown by the yellow region. This spectrum is called the extraterrestrial spectrum. Note that the gray line represents the spectrum of a black body radiator at a temperature of 5,800 kelvins. This demonstrates that Planck's formula gives a reasonable estimate of the solar spectrum as discussed in the previous block. The red area reflects the spectrum arriving at the Earth's surface. As you can see, a significant fraction of the spectral power density is lost by traveling through the Earth's atmosphere due to scattering at and absorption by molecules and particles in the atmosphere. The UV part of the spectrum is absorbed by ozone in the atmosphere. In the infrared, oxygen, water and carbon dioxide absorbs light. They take big bites out of the spectrum. It means that the total power density arriving at the surface depends on the absorption path length of the light traveling through the atmosphere. On average, around 20% of the solar irradiation is reflected by clouds, 6% by the molecules in the atmosphere and 4% by the Earth's surface. So in total 30% is lost due to reflection. 90% of the irradiation is lost due to absorption by clouds, particles and molecules in the atmosphere. 51% of the irradiation is absorbed at the Earth's surface. As the absorption is a loss mechanism, the path length of the light traveling through the atmosphere determines the amount of scatter and absorption losses. At the equator, the light has the smallest path length through the atmosphere. However, at high latitudes, the Sun has a larger path length through the atmosphere. As a result, the absorption and scattering losses are higher at high latitudes. The path length of light is defined by the optical air mass. An air mass of 1 corresponds to the smallest possible path length, which is the path length at the equator. An air mass of 1.5 means that the absorption path length is 1.5 times larger than that at the equator. The air mass can be calculated by the formula 1 over the cosine theta, where theta is the latitude in degrees. An air mass of 1.5 would correspond to the average path length that the light would travel through the atmosphere at a latitude of 48.2 degrees at noon if we ignore the seasons. In week 3, we will discuss how to determine the performance of solar cells using solar simulators. These are lamps which try to simulate the solar spectrum as close as possible. It has been decided that the standard test conditions for the solar spectrum has the spectral shape of solar light with a path length of AM 1.5 through the atmosphere. Secondly, the irradiance of this spectrum is 1000 watts per square meter. As the AM 1.5 spectrum is very important to the solar community, I will use it to demonstrate the relation between the spectral power density function, the irradiance, the spectral photon flux and the photon flux. Here, the spectral power density of the AM 1.5 spectrum is plotted. As discussed earlier, the irradiance is the integration of the spectral power density function over lambda. This means that the area below the AM 1.5 spectrum in this figure corresponds to the irradiance. The blue line is the integration of 0 up to lambda, and you see that the area below the spectral power density up to 4000 nanometers is equal to 1000 watts per square meter, as expected for the AM 1.5 spectrum. The irradiance tells us something about power per unit area. However, we can consider light as a number of photons as well. The photon flux phi is the amount of photons per time per area. Similar to irradiance, the photon flux does not contain any spectral information. For that, we define the spectral photon flux, which is the amount of photons per unit area, per time, per wavelength range. What is the relation between the spectral power density and the spectral photon flux? For that, we only need the energy of a photon as shown in this equation. The spectral photon flux at wavelength lambda is the spectral power density at wavelength lambda divided by the energy of a photon with wavelength lambda. The photon energy is determined by the product of Planck's constant and the light velocity divided by the wavelength. This gives the following relation between P and between phi. So if we integrate the spectral photon flux over lambda, we get the photon flux. In this graph, the spectral photon flux is presented. The area under this graph represents the photon flux. The blue line shows the photon flux in the AM 1.5 spectrum up to the wavelength lambda. It shows that up to 4000 nanometer, the AM 1.5 spectrum has a photon flux of 4.3 times 10 to the power 21 photons per second per square meters. As we will discuss in the coming 2 weeks, every photon can result in one collected charge carrier. This means that the amount of photon flux of these solar spectrums in theory determine the maximum current per area we can generate with a solar cell. So the concept that light can be described by quantized packages of energy, as proposed by Einstein, is a very important tool to calculate the maximum possible conversion efficiencies of solar cells. The average annual solar irradiance on Earth varies depending on the location, as you can see in this figure. A useful tool in expressing the local solar irradiance is sun hours. 1 sun hour equals the energy of 1 kilowatt-hour per square meters. Or with other words, an Earth's surface that is exposed for 1 hour to standard test conditions irradiance of 1000 watts per square meters. Why is this a handy unit? It is related to the fact that the performance of solar modules is quantified under standard test conditions. If a module has a power of 100 watt peak, it means that the module delivers under AM 1.5 solar irradiance of 1000 watts per square meters 100 watts. The addition peak means the maximum power a solar module can deliver under standard test conditions. How do we calculate the average energy yield of a solar module? Let's take again a module of 100 watt peak. In the Netherlands, the annual average solar irradiance is 2.7 sun hours per day. It means that a module in the Netherlands delivers 100 watt peak times 2.7 sun hours is 270 watt hours per day. This equals 98.6 kilowatt hours per year. In sunnier places like Spain, common irradiance can be around 4.2 sun hours per day. This means that the same 100 watt peak will deliver on average 420 watt hours per day in Spain. On a day with a clear sky, the irradiance reaching the Earth's surface is typically in the range from 700 to 1300 watts per square meter at local solar noon, depending on the latitude, altitude and time of year. On a cloudy day, the spectral composition of light is different from that of a light on a clear day. Namely, on a cloudy day, represented by the black line, the relative amount of UV is less and the relative amount of infrared light is higher. That happens because the shorter wavelengths scatter more strongly. Up to now, we have only considered the light coming from the sun and directly incident on the Earth's surface. However, as mentioned earlier, 26% of the light is scattered in the atmosphere. This means that the light falls under various angles on a horizontal surface. The amount of solar radiation that falls on a horizontal surface is characterized by global horizontal irradiance. It's the energy that comes from all directions indicated by the dark blue line. It consists of direct normal radiation from the sun, indicated in green, and the diffuse radiations from the sky, indicated in red. In weeks 7 and 8, we will talk about PV systems. You have to realize that the response of a PV system differs between diffuse light and direct light. This week, I would like to show you how we can measure the irradiance of direct light and diffuse light. For that, we use a pyranometer, and you often see these tools installed next to a PV system. These are instruments used to measure the heating power of radiation. Pyranometers has a field of view equal to the complete hemisphere and is sensitive to the full spectrum of solar radiation in the range for 300 nanometers to 3000 nanometers and has a flat spectral response in the whole range. It allows to measure the radiation very precisely independent of the wavelength of light. It measures the thermal effect of the radiation. Pyranometer consists of a black thermopile detector that absorbs light in the whole spectrum range. When light is absorbed, the black surface of the detector heats up and the increase in the temperature is proportional to the amount of radiation. This temperature difference is transformed into an electrical signal by the thermopile and can be easily measured. The special hemispherical glass dome has the function of spectral filter. It limits the spectral response from 300 to 2800 nanometers, cutting off the part above 2800 nanometers while preserving the 180-degree field of view. Direction radiation from the sun is measured using a pyrheliometer. A pyrheliometer has the same principle as a pyranometer. It also uses a black absorber and thermopile detector to measure the amount of radiation. But it only can see the sun as its field of view is limited to 5 degrees as you see in this movie. To keep the peer heliometer pointed continuously at the center of the sun, the instrument must be mounted on a high accuracy automatic sun tracker. In accurate measurement stations, diffuse radiation is measured by fitting a pyranometer on top of the sun tracker and a shading assembly that moves with the tracker to always block the direct beam radiation reaching the pyranometer, as you can see in this movie. A typical clear day data would look like this. Direct light in green is dominant over the diffuse light in red. In the next example, the morning was clear until 9 AM, when some clouds passed overhead. The direct radiation decreased intermittently and the diffuse component increased. By 1 PM, the clouds completely eclipsed the sun and all radiation was diffused. The green line is nearly zero and the blue line and the red line coincide. Summarized, I hope that I have given you some general insights into solar energy this week. In the last 2 blocks we have discussed the various properties of solar light that will be important to understand the various concepts on which solar energy technologies are based. So let's start using the solar light. Next week I will discuss the fundamental properties of semiconductor materials. We will answer questions like: what is the band gap of a semiconductor? How do we excite charge carriers, and what are the transport mechanisms of charge carriers in semiconductor materials? How do we use semiconductor materials to make photovoltaic devices? See you next week.